My name is Dr. Guy Gratton. I'm an Associate Professor of Aviation and the Environment at Cranfield University in Bedfordshire. I work across aeronautical engineering and environmental science, and in particular I've been working recently with the Light Aircraft Company here at Little Snoring in Norfolk on a project called EnabEl, Enabling Aircraft Electrification, which has included developing and test flying this aircraft, the Sherwood E-KUB, which has been Britain's first designed and built all-electric conventional aeroplane. The Sherwood E-KUB is part of a broader project called EnabEl, which is run by a consortium of 4 organisations: Cranfield University, the Light Aircraft Company, Flylight Air Sports and CDO Squared. This was the first aeroplane to be built, the Sherwood E-KUB, which is now 17 flights into its flight test programme. The second aircraft is getting close to its first powertrain ground testing and then flight testing, which is the electric Skyranger Ninja, based with Flightlight's factory at Sywell in Northamptonshire. And the whole objective has been to learn the fundamental lessons of how to build, to fly, to test and to certify an electric aeroplane, and it's been a British-centred project, so it's been very much about creating British intellectual property that can lead to ultimately British aircraft and British jobs building them. So we now have a good idea of what the performance of the Sherwood E-KUB will be. It's best defined in terms of the altitude it can climb to and the range it can fly. So if we climb to around 1,000 feet, the aeroplane's capable of flying probably for about an hour and a quarter at about 45 knots. So that's going to give you round about 60 nautical miles, about 70 statute miles, plus another 30% safety reserves on top of that. If we climb up to 2,000 feet, that's going to come down to around about an hour, so about 45 nautical miles. If we want to really go for altitude, the aeroplane will probably climb to around about 7,000 feet. We haven't tried quite that high yet. We have been up to 6. And by the time you've reached 7,000 feet, is probably the point where you need to think about turning right round and going back and landing where you took off from. So the test flying of the aeroplane so far has concentrated on the basic system integrity. So we've now got to the point where everything works, it all works together, the aircraft performance is acceptable, the safety of the aeroplane is established. It is probably at a point now where an ordinary PPL could get in and fly this. The next stage of the flight test program is performance based. So we're learning to create the performance manual for an all-electric aeroplane in terms of climb performance, cruise performance, takeoff and landing distances as a function of battery charge, air temperature and so on, in ways that haven't been done before. We know how to do this for a conventional aeroplane, but we don't at the moment know how to do this for an electric aircraft, so we're learning how to do that. That will also involve testing of failed components. So failure of the selectable throttle backstop, so going to 0 power and increasing power again and seeing how it behaves. Failing a single battery pack, possibly we may go as far as failing 2 battery packs and seeing how the aircraft's performance maps and how to teach pilots to safely operate the aeroplanes. So that's the next stage. The following stage after that, we're going to be putting more instrumentation in the aeroplane, and we're going to be doing a bit more of a pure research related to how to instrument up an electric aircraft and how to measure things. And if we get the funding for the next stage after that, which is a program called EGYPSI to develop a British 65 to 100 kilowatt electric powertrain, the E-KUB is going to be used as the test bed for the cockpit instruments for that, which will then go into a larger aeroplane. The electric powertrain on the KUB here behind me, actually it's fairly low powered compared to what we can currently do with an internal combustion engine. So it's 28 kilowatts, which is equivalent to round about 40 horsepower. The Herth F23 we've got in the next hangar in a similar aircraft is a little over 50 horsepower, so unsurprisingly we get a poorer climb rate. Overall we're averaging around a 360 foot a minute climb rate, out of the E-KUB, whereas the Hearth-engined aircraft is giving us initially around about 700, although the drop-off with altitude is less with the electric engine than it is with the conventional engine, because of course it's not breathing air and therefore it's not affected by air density as much, although it is partly affected because it's still got a propeller. Yes, there is some redundancy. There's 5 battery packs and the aeroplane will fly on 3. We've got a second throttle control and some of the wiring is duplicated. A lot of that was mainly because we wanted to do these things to learn from. So as we go through in the flight test program, for example, I'm going to be deliberately shutting down a single power pack at least to learn how to fly with reduced power, what the implications are for the operator's manual and performance data and so on. As we go forward, I think you can expect future electric aircraft to have more routinely duplicated wiring, possibly duplicated controls. They will certainly continue with this approach of duplicated battery packs. The analysis we've done suggests the perfect number of battery packs is probably 3. This aircraft's got 5 because that was the size of batteries we were able to use at the time. The electric Skyranger Ninja that's coming after this, that will use 4. That number being a compromise between the ideal 3 and our weight and balance requirements. So what am I thinking about when I'm flying this compared to a normal engine? With a normal engine, of course, I've got fuel controls, mixture controls, carburetor icing to worry about. None of that is an issue on the electric powertrain. In the early days of testing of this aircraft, we did worry a lot about cooling. That's now solved. If you look at the latest version on the nose, you can see a really big air intake, and that's all for cooling the motor. So this has really taken it to the point where mostly it's very much carefree handling. More power, less power, occasional glance to make sure the temperatures are fine, but they always are now. Only significant point we have to consider that's new compared to a conventional engine is that on a conventional engine, if I close the throttle completely, I've still got some fuel going in, I've still got some power, and the propeller is still going round. Whereas if you close the throttle on this electric powertrain, the propeller stops, I've got no power into the motors whatsoever. And to then get it going again needs a trickle of power for a few seconds. That is new, and that worried us quite a lot with regard particularly to the go-around. So if I've got if I were to fly an approach with 0 power and then I suddenly needed to do a go-around, I need that power straight away. So what we've done here is we've introduced something we call the selectable throttle backstop, or STB, very similar to what on a turboprop would be a flight idle stop. And what that is I select it before takeoff, and then that ensures that I can't get 0 power. It comes back, the current setting is at about 300 watts, and that's just enough to keep the propeller continuously rotating so that when I need full power, I've got it almost straight away. An additional benefit from a ground safety viewpoint is, although it's relatively slow, the propeller is always going round, so it's much more obvious to anybody around the aircraft that I've got a live system, and therefore they don't want to come anywhere near the propeller. What's the effect of the electric powertrain on noise in the cabin compared to a normal engine? It's less, but it's not enormously less than we're used to. If you take a normal aeroplane, the piston engine and a propeller, about 20% of the noise comes from the engine and about 80% comes from the propeller. With this powertrain, the motor is almost silent, but the propeller is still a propeller. And that's true whether you're talking about noise as heard from the ground or noise as heard in the cockpit. We've probably got about a 20% reduction in how loud it is because we've lost the engine noise, but we've still got the propeller noise, and that's still transmitting itself through into the cockpit as well. So I'm sat here in the cockpit of the E-KUB, so let's have a little look at what the controls are and do. So this is obviously the control column, exactly the same as any other aeroplane. These two are the main wheel brakes for the left and right main wheels, so I can use those to supplement a turn as well as just braking straight. Down here is the throttle. This works normally just like a normal aircraft throttle, although inside here is actually a potentiometer. This we call the STB, or selectable throttle backstop, and is equivalent to a flight idle stop on a turboprop engine. So with that selected, I can't quite stop the propeller, whereas if I flip it up, I can stop the propeller, which I aim to never do in the air, only on the ground. This down here is a normal pitch trimmer. If you look here at the instrument panel, we'll talk about what the flight and engine instruments do. These two are absolutely standard aircraft instruments, an altimeter and an airspeed indicator. Then over here, this is an AV30 combined flight instrument. So it's an artificial horizon. I've got a duplicate airspeed indicator here. I've got a duplicate altimeter here. So they're duplicating what's going on here. Also a slip ball, which duplicates the mechanical one down here. And I've got the ability to set barometric pressure. I've got a voltage indicator for the power system. And critically, I've also got a direction gyro here that basically allows me to know which way the aircraft is flying, because we've learned that it's really hard to get a normal magnetic compass to work with the electrical system in front of here creating a magnetic field. So we had two choices: either go for something that's basically a gyro and GPS solution, or put a remote sending compass with a sender probably in the tail or on a wingtip, and we decided this was our preferred way of working. That's the flight instruments. Now let's have a look at the powertrain. So this is a battery control unit. The system is not functioning at the moment, which is why you've got lots of red flashing lights, but I've got 5 banks here for the 5 battery packs, and each one of those, so I've got numbers 1 and 2 are in my port wing, number 3 is in the nose, numbers 4 and 5 are in the starboard wing, and I can turn it all on together simply by pressing that button for 2 seconds and releasing it, obviously with that guarded switch on. This right-hand bank at the moment does nothing, but as we go forward in the flight testing, what I'm going to be doing is having one of those battery packs connected to the right-hand array, so we can turn that off and go from 5 to 4 battery packs as a way in flight test of simulating a battery pack failure. This button down here is called the E-stop. It doesn't affect the primary controls, but if we push that, what happens is that a switch tells the inverter in the nose to stop providing power to the motor. So if I've got anything goes wrong and I'm worried about the power going into the propeller, I can hit this straight away and that will automatically stop the propeller, but I only need to rotate it and then close and reopen the throttle, and I've automatically got power back into the motor again, much faster than if I go into a software reset on the systems here. We also use this as a ground safety device because with that pressed, the propeller can't go round, and therefore when we're doing anything on the ground with the power on, including charging the batteries up, having that in is a safety measure that ensures that somebody can't accidentally set the propeller rotating and possibly injure someone outside the aeroplane. So on the right here, this is the Geiger ADI unit. This is how, when we're flying the aircraft, we monitor what the powertrain is up to. So some simple numbers up here, a nominal range on the current charge and what time it is. Then this shown 90 on a scale of 0 to 100, so that's my percentage state of charge. It's a bit like how much fuel I've got in, which is also as an absolute value 288 amp hours. Batteries are at 57 volts, which is where they should be when it's around approaching fully charged. I've got temperatures for the battery. Here's 19 Celsius. Motor is 11 Celsius. Motor controller is at 12. Power here is showing it's toggling around about 700-800 watts, and you notice there's no sign, so that means the battery is actually at the moment they're on charge on the ground. When we're flying, I will see a minus sign because it's discharging the batteries, and typical numbers I'm looking at around about minus 300, minus 400 when the throttle's closed. When I'm taxiing, depending on the slope and surface, between about 600 watts and 2000 watts. Takeoff power is going to be around about 25 to 29,000 watts. And in flight, I'm usually somewhere between about 10 and 15, depending on the conditions I'm flying at. There's various touchscreen aspects here that also allow me to go in and look at individual systems if I need to, but for most purposes I just use this basic screen. And then to the right of that, it's not fitted at the moment, we've got a bracket here that will normally carry our radio, and then the cables here connect to an antenna that's at the back of the aircraft to keep it away from all the powertrain electrics and free of interference. So that is the cockpit of the Sherwood E-KUB. So what have we learned through this project? Huge amounts, because we'd never built an electric aeroplane like this before. So we've learned a lot about how to integrate the motor, the controller into the aeroplane. We've learned how to design the cockpit controls. We've learned some small things about how to lay out the cockpit, about where to put the cabling for the radio antenna to make quite sure that it's not being interfered with by the motor. We've learned it's incredibly hard to get a compass to work, and in the end we gave up and replaced it with a GPS-based direction indicator. And probably the single biggest and most important thing is all the lessons we've learned about what the safety standards need to be. So we've created a huge amount of work on electric aircraft safety standards, which has been developed with the British Microlight Association and with the Civil Aviation Authority, and more recently with the Light Aircraft Association. And that work, which we will be putting in the public domain sometime soon, is going to be really critical for the whole future of electric flight, because we've been working to define what the safety standards need to be for an electric aircraft. And of course this is fundamental to why we've done this aeroplane, because this is not, yes, I believe this aircraft is going to be available to people who want to buy one, but it's also very much a learning platform to allow the big team to develop our understanding of how to deliver a safe and effective electric aircraft.